All right, so we're going to do problem 46 from chapter 7. A loaded cab, so this is a diagram. A loaded cab of an elevator has a mass of 3 times 10 to the 3 kilograms and moves 210 meters off the shaft in 23 seconds at constant speed. At what average rate does the force from the cable do work on the cab? So you want to find. So what is that? What does that mean? The rate does the force do work on the cab? So you want to find the energy per the work done, the work done by the force per second. So in other words, you want to find power, and power is defined as the amount of work done by the force divided by the time interval. Okay, so this is definition of power. So let's look at this diagram. So you have the cab with the weight, and it's being moved up. It's moved out 210 meters. So during this during this move, there's a change, right? There's a change in distance, and also there's a change in gravitational energy. So let's look at the free body diagram. So this is the cab. Experience gravitational acceleration, and also its own weight is gravitational force, which is mg. And because the whole thing is moving at constant speed, which means that this force has to be balanced by the force from the cable. So these two have to be balanced each other. Okay, so this is the amount of force that has to apply to this thing to move it up and moving at a constant speed. And during the move, it has moved 210 meters. So you can see that your F should have the magnitude that's mg, and it should be pointing upward, right? Just by looking at this diagram. So it's pointing upward, and the displacement is going upward as well. So what is the amount of work done by the force? The amount of work done by the force would just be mg, and then times the displacement d, okay? And the time is also given, so you can readily use this equation to calculate the time rate of change of the energy, or the power of the force. How what is the work done by the force per second? So you have the mass, which is this magnitude. You have 9.8. You have 210, which is the distance, and over the time interval, which is 23. So after you do this calculation, you should have your the power that has a numerical value of 2.68 times 10 to the 5th, and that's in watts. Watts is joules per second. Okay, so this is a basic, a very simple problem that utilizes the definition of power, which is just the work over the time interval. Okay, and the next one we're going to do is 62. So let me draw the diagram first. We have this, and then going to here. Okay. All right, so problem 62. A 250-gram block is dropped onto a relaxed vertical spring that has a spring constant that's 2.5 newtons per centimeters. So the mass of the block is 250 grams, and spring constant is 2.5 newton per centimeters. The block becomes attached to the spring and compresses the spring 12 centimeters before momentarily stopping. So in other words, the distance that it has changed when the spring is compressed, that distance, we call that d, is 12 centimeters. Okay? And so while the spring is being compressed, what work is done on the block by gravitational force? So you want to find work done by gravitational force, which we use Wg, and what is the work done by spring force? So Ws, and what is the speed of the block just before it hits the spring? Okay, so what speed of the block just before it hits the drop onto? Okay, hits the spring, and if the speed at impact is double, what is the maximum compression of the spring? Okay, so let's look at this equation. look at this diagram. So you have the you drop an object, and then it's attached to the and then it is attached to the spring, and then it's going further down. And we found that it has compressed the spring by 12 centimeters, and you have the spring constant that's given. Mass of the object is also given, and you're asked to find the amount of work done by gravitational force. So the gravitational force from the block, so that will be Wg is gravitational force times scalar product of the distance, right? So by looking at this diagram, we know that gravity is going down. Displacement is also going down as well. So we can just use, so they are in the same direction, so we can just use the numerical value of these two quantities. So you have m is 0.25 kilograms, g is 9.8, and then displacement is 0.12 meters. So after you plug in these numbers, you should have the value that's 0.294 joules. Okay? Now, so this is the work done by gravitational force, which is just force times scalar product of force and displacement. And you also have to find what is the work done by spring force. What is the formula for the work done by spring force? The formula is equal to 1/2 spring constant and then displacement squared. So that's the work done by the spring force. So once you have that, so we're given all the information. Your K here is given newtons per centimeter. So you want to convert it to meters. So it's 2.5 Newton, and then your centimeter is 10 to the negative 2 meters. So after you do the conversion, you should have 250 Newtons per meter. So times 250, and then times the displacement, which is 0.12, and you square it. So what you found is that the work done by the spring force is negative 1.8 joules. It is negative because the spring force is a restoring force. It's always in the direction of trying to bring it to the original position. So that's why the work is always negative, done by the spring force. So you're asked to find what is the initial velocity at the impact. So this is a diagram. So let's look at this diagram again. So you drop the box. So that box, when at the contact, there is an impact. So that impact has a velocity which is not given. So we don't know what this velocity is. And then it's going to, because of the impact, and then because there's enough energy, so it's going to continue to compress the spring until the spring, the whole thing came to a momentary stop, which means that the final velocity at this point is 0. Okay, so you have the initial velocity that's unknown. The final velocity is 0. Who provides the so you can see that there is a change in kinetic energy, and by work kinetic energy theorem, we already calculate the amount of work done by gravitational force by the spring force. Those are the only two forces acting on the block. So this is a net work done, net work done by these forces, in the system, and that net work has to be, is used to transfer energy into and out of the system. So we can see that basically it's transferred energy out of the system because initially you have a non-zero velocity, and after some time, then this comes to a stop. So by work kinetic energy theorem, we know that delta K is equal to net work, right? Net work done by the net force. So all this net work, so let's see, net work would just be the work done by gravitational force plus the work done by spring force. So what we have here is that we have 0.294, and then that's the work done by the by gravitational force, and the spring force did 1.8 amount of work. So that's this is on the right hand side. On the left hand side, you have the final kinetic energy minus initial kinetic energy. Now, final kinetic energy is 0 because there's no final velocity. So this is equal to negative 1/2 mass of the box, and then times initial velocity squared. So this has to be equal to this. So this, let's see, do I have the numerical value here? So this is equal to negative 1.506. So you can see that you have negative on one side, you have another negative on the other side, so they get canceled. So after you plug in the mass, which is 0.25 kilogram, then you can calculate your initial velocity at the impact. So initial velocity at the impact will just be 0.23. I'm sorry. The impact velocity is 3.46 meter per second. Okay, so that's basically, this is just the applications of the work kinetic energy theorem. Whatever network that you have is used to change the kinetic energy, and there's an initial velocity. There's no final velocity, so there's a change in kinetic energy. So you need to, in order to use this equation, you need to figure out what is the network done by all the forces. There are two forces acting on this system. One is the gravitational force on the block, and the other one is the spring force. Okay, so then you follow that, then you can calculate the initial velocity. And it also asks you if the speed at the impact is double, which means that whatever speed that you calculated, if we double that, what will be the new displacement? So now, if V becomes known and it's doubled, so let's say your V we calculate to be 3.46. If this now we change it to be like it is doubled, then what will be the the new displacement? So now the D displacement we don't know. How much, what is the new D? So we need to actually, based on this equation, we can set up, another set of equations. So you can see that over here you have your D value here, you have your D value here. This now becomes unknown, and your velocity now here becomes a known quantity. So if we, again, apply this equation, you have delta K is equal to the network. So you have the Kf minus 1/2 and then VI squared, that's equal to the mgd. That will be the work done by gravitational force. That's just mgd, right? And this is positive. And then plus the negative work done by the spring force, which is 1/2 K and then D squared. So you can see that your D now is is unknown. So that's plugging whatever numbers that we have. So you have this is negative. So VI now, so 1/2 0.25 times your VI. Your VI is what is your VI? If you double that, so if you double that, so that, let me just write it. So it's 2 times 3.46. So that's your V, square it. And that has to be equal to your mass times 9.8 times D, and then minus 1/2, and your K value is 250, and then times D squared. So you can see that now it becomes a quadratic equation with a D that is unknown. So calculating this value and rearrange this equation, you should get 125 D squared minus 2.45 D, and then minus 5.98. And the whole thing is equal to 0. So by using the quadratic equation, you can calculate your D value. So your D value is equal to 2.45, and then plus or minus 54.735 over 2 times 125. Okay, so then you have your D value. This one, the negative definitely is not does not work. So you can you don't have to consider that. So it's 2.45 plus the 54.735 over this over the 2 times 125. That will give you 0.2287 meters. So this is the new displacement on the spring. Okay, when the velocity double, you can see it can continue to be compressed, further down. Okay, so that's basically, a problem that illustrates the change of energy, by the amount of work done to the system.